Hello everyone, thank you for signing up and for watching this wherever you are. The objective today is to provide a summary for the exercises that were completed, the critical thinking questions that were completed for chemical activities 7 and 8 in Physical Chemistry, a Guided Inquiry by Moog, Spencer and Farrell, Atoms, Molecules and Spectroscopy. From Chemical Activity 7, the Hamiltonian operator was developed, and we took into account the kinetic energy and the potential energy for the electron. Secondly, we anticipate that the radial distance, the distance r of the electron from the nucleus, may vary in this particular case. This leads us to the radial distribution function. This adds some difference to the solution to the Schrödinger equation for the hydrogen atom when compared to the rigid rotator. The wave function, psi, that comes out from a solution of the Schrödinger equation is made up of three parts. R sub NL multiplied by capital theta sub LM times capital phi sub M. When we look at the solutions to the Schrödinger equation, when we look at those wave functions, we recognize those functions are made up. They're made up of a polynomial in R, that is r to the 0, r to the 1, or r squared, multiplied by an exponential decay in terms of r, such that the e is raised to minus r over 2a, where a is equal to the Bohr radius. In Chemical Activity 7, we explored some graphs of the wave function psi as a function of the radial distance r for some simple wave function solutions. We also explored the dumbbell shape of the 2p sub z wave function. In Chemical Activity 8, we start with a reminder of eigenvalue equations, and we also recognize that the solutions to the operators L hat squared and L sub z, the solutions to those operators are the same as the solutions that we encountered for the rigid rotator. We also talked about if psi NLM is an eigenfunction for a given operator, then the state of the system has a definite value for the physical property represented by the operator. That of course means that if psi NLM is not an eigenfunction, then the physical property does not have a definite value, although we can figure out an average value, and we looked at that through the expectation value calculation in earlier chapters of McQuarrie. As we wrap up Chemical Activity 8, we explore angular momentum in the hydrogen atom. We recognize again a lot of similarity regarding our work with angular momentum for the rigid rotator. We further explored the radial distribution function, and lastly we talked about the energy levels, quantifying those energy levels and quantifying the transition energies between those energy levels, again for the hydrogen atom. Thank you for listening. We will press on with a further review of Chapter 7 in a subsequent video. Thank you for listening.